How you doing, guys? Today we're going to talk a little bit about sight and light and how we... What? What is that? I have a little visitor. Hold on 1 second. He's so cute. Do you see him? He's a little frog. He's so cute. I'm going to try and catch him. Just slowly. Ah, whoa. What's happening? Look at that. I got this little frog in a disc, and I can make him disappear, and I can make him reappear, and I can't touch him. What exactly is going on there? So just take a look around you right now. Look around the room. What is it that you see? You see tons of images. You see colors. All of these are updated as you turn around and as you move your head. Every time your attention is redirected, your brain and your eyes, or I should say your eyes and your brain, updates these images, the light that is coming into your eyes. Now, we see all these images essentially in a seamless transition, but in reality, our eyes are taking in these images at such a fast rate that it is near impossible for us to even notice the difference. Now, some of you may have noticed those differences before. Now, even though, I'll talk about that momentarily, but even though we keep seeing all of these images, I want to buy the best high-def TV, our eyes are the best high-def image we can actually see. The range of colors that most of us see are seamless. The quality is impeccable. And unless we can notice that frame rate that is changing, which again I'm going to talk about momentarily, we see this as a seamless transition of perfection into the world. So now this seamless transition that we were talking about is obviously how we sense light. Now just a quick review of things we should know. We have two light detectors. Well, most of us have two light detectors. Eye number 1 and eye number 2. Yes, they are called eyes. That one's creepily moving slowly. All right, so our eyes work kind of just like a camera, or if you're my age, a camcorder, or your camera on your cellular phone, and we're going to talk about that momentarily. They are really detecting all of this visible light at such a fast rate that we can't make up any choppiness. We just see this one seamless image. Now, the light that we see is not the entire electromagnetic spectrum. It's actually the smallest part of that electromagnetic spectrum, as you can see here. It is the visible light spectrum. You've learned that there are other types of waves. All we can physically sense, or see I should say, with our eyes is the visible light spectrum, otherwise known as the rainbow, Roy G. Biv, or red, orange, yellow, green, blue, indigo, and violet. And you, just like me, none of us have any idea what color indigo is. It's just part of our rainbow. So, the visible light spectrum contains a range of wavelengths. Now, these wavelengths are really small. 400 nanometers, that is some number, 400 times 10 to the negative 9th meters, all the way to 700 nanometers. And if I just go back, we can see that red light is the 700 nanometer range, and blue light is towards the 400 nanometer range. And that gets important later, like why is the sky blue? Here we have it, again, 400, 700 nanometers. And now, as I said, this seamless transition may not always be so seamless. So this is going to be a little long, but check this out. Here I've got my car. We're about to start the car. Gonna play some tunes. This is awesome. And focus on the wheels. Now I'm driving, and look at those wheels. Those wheels are going forward. This is awesome. I see with my eyes those wheels going forward. And now they're going backwards? The heck, they're going backwards. And now they're like stopping. This is freaking me out. But now they're going forwards again. The car was just getting faster. I don't understand. How is this happening? They're going backwards again. How is this happening? Let's check out a different view. It had to be just the view. All right, cool. Wheels going forward. Wheels are going forward. This is perfect. And sugar. They are kind of going backwards now. Yeah, they're going backwards. I'm a little freaked out. They're going backwards. Wait. All right. They're going forwards again. They're stopping. They're backwards. What the heck is going on? We've all seen that take place. Now, this video goes on for a few minutes, and what exactly is happening? Well, this is one of those reasons why our brain and our eyes aren't matching each other. So, our eyes are literally little cameras taking a picture about one picture every 60th of a second, or at a frequency of 60 hertz. It is a refresh rate of 60 times every second. So what happens with that? Well, the spokes on the wheel, we take a picture and we take a picture and we take a picture. And if that picture on our eye, we see the wheel spoke here in that picture. And now we look at the very next moment, our eye takes that picture. It might be a little backwards and a little backwards. So if it's going backwards, it's just happening that our brain is catching those images where it looks like the car or the wheels are going backwards. This is an example of our brain playing tricks on us. Now, this happens all the time with optical illusions. So do you see here, do you see a face, or do you see the word liar? L-I-A-R. Both of them are there, and now that I've said this, you're probably seeing both. Let's talk about that for a moment. All right, so the first image, or the first type of illusion, is the one I just showed you. That's a literal optical illusion. A literal optical illusion is actually when we have two different images that are just in the right place. They're like strategically placed such that we can see one or we can see the other. So it is literally your brain playing tricks on you of what image it wants to focus on. It's kind of like a reversible image, right? So like a reversible jacket, I could see one, I could see the other. Well, that's probably a bad example, but this is literally like, what did I focus on? If I point one thing out, you see that. If I point the other thing out, you see that. So that is what a literal illusion is. Then there's this thing called a psychological illusion. Now, psychological illusions are a little bit more complex, and they rely on overstimulation of your brain. So my eye, just like that car, my eye was trying to see as much as possible. The dimension, what's going on. And because it's trying to take in so much, it gets confused. It doesn't know what to focus on. So like this is if you have a mismatch of geometric objects, or maybe a bunch of lines that when you shake your head back and forth, it kind of confuses it and it seems like there's some motion. That's a psychological optical illusion. Then there's the cognitive optical illusion. You've all probably seen these in movies. Like you take some liquid or some sauce, you squish it, and then there's this pattern. And what do you see? Well, this type of illusion is a cognitive illusion because it's messing with what we call your cognitive ability. It's different than other optical illusions because this is really relying on your subconscious, on what you see. So it's kind of like if you see positive space or negative space. Now, we're just going to go through a bunch of these because they're kind of fun and you can see them. So I thought it best to just show you these pictures without my pretty face just getting in your way. The easiest way for you to do this is pause the video so you can really stare at the image and then move forward as you go. I'm going to go through them kind of fast. So next we have is the left center circle bigger than the one on the right. They are in fact the same size. Yes, whoops, yes, this circle is the same size as that circle. Measure it if you don't believe me. Are these spirals? They are in fact not spirals. They are just a bunch of circles independently drawn, one on top of the other on top of the other. These are kind of cool. Just keep staring at the black dot in the middle of the screen, and as you can see, eventually that haziness is going to go away. Totally freaky. This one's also really cool. This kind of puts an image in your brain. If you stare at the black light for 30 seconds, count them, 30 seconds, 29, 28, etc. Then stare at the white spot on your screen. All of a sudden, it's going to glow like a light bulb. Really cool. How many colors do you see here? Like 1, 2, 3, 4, 5. Yes, that's right. There are only 3 colors: white, green, and pink. They just look different because of where they are. Count the number of black dots. Pause this one for a long time. It's going to take you a really long time. But if you're like me, those black dots keep moving. Are these lines horizontally parallel or do they slope? They are in fact parallel. Trust me, I use the ruler. You should too. I can't even do this one. How many legs does this elephant have? I know the answer is less than 100, but the legs keep moving. Really weird. Is the blue on the inner left back or on the outer left front? Yep, that's right. This blue might move around. A little weird. Now, do you see a musician? Totally. Or do you see a girl's face? Now, if you look at the black dot in the center and you move your head back and forth, whoa, that's kind of freaky. Do it as many times as you'd like. Now, hopefully, as you went through, you could identify which type of illusion that we were talking about. Again, they're all different versions of illusions, how my brain, how my eyes perceive things. So now I know what you're thinking. You're thinking, Mr. Rose, are there other types of illusions? I remember that frog, that didn't seem to fit into one of your categories. So let's examine the frog. In my little, look, the frog is real. Here's my little froggy frog. And the frog exists in 2 different mirrors. Ready? Check this out. This is a concave mirror. And here's another concave mirror with a hole in it. Now, when I put them together, we're going to talk about in the future concave and convex mirrors and lenses, and that is one of the reasons what helps us see. Also, fun fact, unrelated, did you know that it is actually true? You've heard it, but it is true. When you see images and they go through your eyes, which act like lenses, they're actually imprinted on the back of your eyeball upside down, and yes, my brain does interpret them and flips them right side up. So that is something true. Now, these mirrors create what's called a virtual image, something that I can't touch, and it seemed like it was an illusion. Made an illusion out of my little frog. Now I know what else you're thinking. You're thinking, Mr. Rose, I've heard of something else. I think it was called a stereogram. Well, if you're as old as dirt as I am, you know that stereograms date back to the 1800s, 1838, and that is a different kind of illusion. Now, I'm not going to go and look at the 1838 stereograms. Those are boring. I'm going to look at, with you, some cooler stereograms. Now, this is a really cool stereogram. Maybe some of you have seen these, and maybe some of you haven't. But if you noticed, I took myself out of this picture, so you're not distracted again by me. There is an image hidden in all of these colors. Kind of crazy. Again, pause and try and figure out how to see it. Maybe focusing my eyes, unfocusing my eyes. Look, you have to look through the picture. Now, the stereogram works because most of us have 2 functioning eyes. Now, I also want to warn you, I apologize, if some of us are colorblind, this may be a little bit difficult for us to see. If you're colorblind, this may not work, so I chose a second image, again, which hopefully we can see. Again, take a pause, try and see, and I will be right back to explain just how the stereogram works. Alright, so I will explain how to see those stereograms in our class. But again, a hint was that most of us have 2 eyes, and we see with depth perception. One eye takes an image, another eye takes an image, and it puts those images on top of each other so we can see them. Here's something that most of us can do. Take a paper towel roll or a toilet paper roll, as I have here. put it on one eye like so, and close the other. Now, take your hand and put it right next to the toilet paper or paper towel roll, and look how close it is to my face. Then open up the other eye. Ah! There's a hole in my hand. Yeah, that's right. This paper towel roll or toilet paper roll is going right through my... Oh, thank goodness it is not going through my hand. But my brain perceived it that way. That's because the way that these stereograms work, they're called parallel viewing stereograms. There's another one which is a cross-eyed stereogram, but these were parallel viewing stereograms, meaning my eyes have to look through that picture, and then it produces a 3D virtual image. There's that word again, virtual image, that we can see. It's this really 3D image projected on a 2D piece of paper, or in this case, your 2D screen. They're really kind of cool, and there are tons of them. Back in the 1800s, they were done by placing big pictures specifically distances apart that my brain perceived and tried and did the same thing. So, that is all I have to say about optical illusions and how our eyes can perceive all of these types of light differently. Next time we talk, we're going to talk about lenses and optics and how that works and how the eye actually works. Well, not the biology part, but the physics part. And how we bend refraction and reflect all sorts of light. Eventually, I'll even tell you why the sky is blue. That's it. I hope today was interesting. I hope you had some fun. Share it with your friends and neighbors. What else do you got to do? Catch you guys later.